I equal 1.
You should prove
So,
all I, not just I equal.
yeah, we should prove this for all I.
But for now,
But if the index here is not 3, if this is 1 or 2, and if both indices here are both 1 and 2, then this property comes from the restriction to the rank 2 case.
no, I'm questioning that I should go from 1 to n, not just.
Yes, yes, so this is what I didn't remember before. There is some reason why it is sufficient to restrict to the rank 3 cases that I don't remember now.
But now we look at 1, 2 case only for now.
No, no, we are looking at the case of rank 3. But let me think. So,
We're assuming
No,
that we can
because,
restrict to the n equal 3 case.
you're assuming this because I don't remember why we can assume this.
Because I think it will not, it's the same argument, something like this, it will not change. Something like, well, how was the definition of B? I forget. What was the B?
B are the exponents in
In
the exchange relations, in the two monomials of the exchange relations.
so
So
they will be
if,
the exponents of what? So Bij is exponent of what?
Bij is the exponent of xi in the relations with label
Right.
3 starting from T prime.
Right, right. So it is the same trick because if one is k is not 1 and 2, it will not change. So its exponent will not change, right? It's the same trick as before, as part 1, no? You see my point? You're moving across 1,
No,
2.
The variable doesn't change, but it may appear.
It doesn't change, the exponent will not
Oh
change.
yes, really are.
Eh?
3, 4.
I cannot believe it's me telling you this. It's what you said before to us.
So B, 3, 4. You say that these are always
Right.
equal, might be.
Because the only variables under change are the 1 and 2 labels, right?
But we know how this changes because they are related by mutation. Okay. So, yes, if the indices are different. Oh yes, this comes from the mutation. We know from the mutation that B34 of T2 is equal to B34 of T1 plus, if the index is I, we have B 3I BI4 plus B 3I BI4 divided by 2. So if we prove that all these elements are the same, then these two they are not the same, but answer. I don't know, let me think about this in the next days. I don't want to waste much time now. So look at this as a proof of the theorem in rank 3. And then, I will show you that we can always assume that the rank is 3. Okay. Of rank 3. Okay, so this is what we have to prove. Some notation. We let dm be dm3 of tm, where m is always the number between 1 and 2, which is congruent to m modulo 2. Okay? And I recall you this definition that we use in the rank 2 case, u n plus 1. This is u m of tm, that in the rank 2 cases was q m plus 1 divided by r m plus 1. And this is the same. So u m plus 1 is the quotient of the two coefficients appearing in the two monomials on the edge after u m plus 1 in that order. Okay. So now I need to recall you the recursion satisfied by the coefficients u, v, m in general. u3 of tm plus 1, this is for any m. u3 of tm yes, we have this relation in general where if you go back to your notes, when we have a situation like this, then we can express the ui of t prime in terms of ui of t for all I different from j. And the relation, I don't want to write down the relation, I'll just write down the relation in this case. So we apply this in the case where we have tm plus 1, in the case where here we have 1, if this is 2, it is singular. So in this case we have that m is odd. Okay. So in this case the relation is u3 of tm plus 1 is u3 of tm times u1 of tm to the maximum between b1 3 tm 0 times 1 plus u1 of tm to minus b1 3 of tm. This was the relation that we had proved that we used to show that these coefficients are periodic. Similarly, in the other case, so this is a case where tm plus 1 and similarly if tm plus 1 as a 2, then we just have to replace this index 1 here and here. So from these two relations, we can compute this product j from 1 to h plus 2 of u 8 of t j plus 1 over u3 of j. Of course, this is like a telescopic sum. This is just u3 of ph plus 2 divided u3 of p1 ph plus 3. pH plus 3 is 3 prime. So from this relation, if we divide this relation by u3 of tm, then we obtain the rest, and so this becomes product from m from 1 to h plus 2. Here is j, then there is n. So what do we have? u1 of tm is u1 of tm is u n tm. So this is good in both cases because of course in this case m is odd, and so we have u1 of tm, while in this case m is even, so we have u2 of tm. So it works in both cases to the maximum between these two elements. Here. So this element here is what we denoted dm, d13 of tm.
So what are you substituting now in? I don't understand.
So if we divide this relation by u3 of tm,
also you're
here
taking
we have the product of all these
okay.
quotients. So I have the products of all these.
Okay.
All this.
Yes, yes.
Okay. So that's what I'm going to write. This is the product with m going from 1 to h plus 2. So here we have the maximum between dm.
So again, when you write it says it's u1. I'm confused.
Yes, but we have u1 of tm if m is odd. So if m is odd, this m within this bracket is 1. That was the
And
definition.
if it's even?
If it's even, it's 2. But if it's even, we have this other relation where we have to substitute 1 with 2. So this works in both cases.
Non capisco.
I didn't write this relation, or maybe I can do it. If m is even and the edge is labeled with 2, then the relation is
Same with 2
the same
instead of 1.
with 2 instead of 1. So I have to write u2 of tm to the maximum b23 tm.
Ah, okay. Okay.
So
okay.
in both cases I have u and
It's the
within
same.
brackets.
Yes,
tm.
okay. It's the convention.
Yes. And then 1 plus same u and tm to the minus dm. Okay? This is the same as before. And then we use also the notation un plus 1 instead of un tm for convenience. So we have n from 1 to h plus 2 un plus 1 to the maximum between dm and 0 times u1 plus un plus 1 to the minus dm. So remember that we want to prove that these two elements are equal. Okay, this is the first thing that we have to prove here. So in particular, we have to prove that this is one. Well, this is not easy to prove, so we have to work a bit more. So I will call you another relation that we prove. There are two cases that um plus 2 was 1 plus plus 1 to the dm. We saw this relation the last time where of course instead of p and we had either b or c depending on the parity of m. This is the same.
So the plus was the greatest common divisor, right? Psychologically.
Not necessarily. Yes, but psychologically, yes.
I don't see why this is true. Like
What?
because you're taking the greatest common divisor between 1 and um plus 1. I'm confused. So let us assume that plus is the greatest common divisor. For example, right?
Yes.
So you're taking 1 plus um plus 1. What is the greatest common divisor? Well, that is
Depends on plus 1.
between 1 and a something. The greatest common divisor depends on the something. One is
Because it's not really the greatest common divisor. You have to take the maximum of the exponents, but this may have negative exponents. The minimum of the exponents, but this may have negative exponents.
So you have to take the minimum of exponents, right?
Yes.
Okay.
So if they are both positive, it's the greatest common divisor. But
I see. Okay. So 1 plus 1 is all 0 exponents, right?
yes.
Okay. So what you're saying here, okay, so slightly.
All these elements cancel at the end.
Yes, now it's counterintuitive because assume that all exponents are negative, right?
Maybe it's not possible.
Yeah, you're proving it's not possible. No, I'm asking.
Yeah, of course, I'm proving that this is 1. So if the exponents are all negative, I don't know, because then here we have the
it's
negative
complicated.
exponents, so it might be close enough. But the proof is very tricky, you will see.
Yeah.
So then, I think we don't need this.
Yes, in one case you
Maybe
will have
I
to
deleted
prove,
the statement.
in one case you will have to prove something about the structure of um plus 1, right? You have to know what is that. It depends. No? You have to go inside the
We have to go inside the
You have to go inside the It's not a cheap thing.
Not that deeply, but we have to go inside the dm now.
Well, dm positive or negative, that's all you care about.
Now we need to show that the dm are also periodic.
Why? Because dm appears in both the terms. You need to know they're periodic.
No, there might be an alternative proof, of course.
No. I have a question which is more deep than this. Is like that.
I didn't try to find an alternative
No,
proof because
the product is not 1. It has to be 1. But it's not that each term will be 1 in the product.
No.
Okay. So it's more complicated. Okay, that was my question. I could not formulate. It's not that each of them is 1. It's the product of all that.
Yeah, because these terms are just these portions. So if we show all these elements are 1, that we prove that all these are equal, which is not true. Just periodic of previous ratios.
I see the point. Okay, no, thanks. That was my question. I could not explain, but okay.
Yes. Also in the rank 2 case, it's not true that these are
okay, it's clear now.
So, we recall from the matrix notation. Matrix notation. B2, 3. So maybe I'll just do the case where n is even. The other is similar. When we mutate from Tm to Tm plus 1, we have that B23 of Tm is minus B23 of Tm, Tm plus 1. Now, this happens when one of the two indices here is equal to the level of the edge. Right, in the other case, B23 of Tm plus 2, Tm plus 2, we want to look at this notation. So that in this case, these vertices are joined by an edge labeled with 1, which is different from 2 and 3. So we have to apply the other formula for the notation. This is B23 of Tn plus 1 plus B21 Tn plus 1 times the maximum between B1, 3 Tn plus 1 and 0. So, yes, the formula in the notation was not exactly this, but we saw several times that this is an equivalent reformulation. So, we sum up these two relations, and we obtain B23 of Tn plus B23 of Tn plus 2. These two cancel. So we have B21 of Tn plus 1 times the maximum of B13 Tn plus 1, 0. Yes. Now we look at the definition of Dm. So B23 of Tm is Dm. We are in the case where n is even. Plus, this is Tn plus 2. So here B21 of Tn plus 1, what is this? If n is even, this is the same as this is the same as B21 of T1, because these two exponents, so the two exponents B and C changes sign at every step along the path. We saw this in the rank 2 case. So in particular, if since n is even, T1 and Tn plus 1, these numbers are the same. You know, in the mutation, at every step they change sign. So if they have the same parity, they are equal. So this is by definition, this is what we call B1, beginning, times
We
maximum.
call it B2.
B2, you're right. B2, yes. Times the maximum, B13 of Tm plus 1, here m plus 1 is odd, so this is Dm plus 1. So if m is odd instead of even, we can do the same sort of computation, and we obtain here Bm instead of B2. So we obtain B1 instead of B2, and so the formula becomes just this. Okay? Oh. So this is what we have to prove to B1. Yes. Now, we have to look at these two formulas here. This formula and this formula. Are they similar? Do you think that one of them is a particular case of the other?
Posso dire gli esponenti, è un disastro.
So let's see. If we consider Z as a semi-field with the product is plus, and the additional sum is the maximum.
Mm. Okay.
What is this? This becomes P. Huh?
There.
Let me see.
So Z
So
is
this
what?
becomes Dm
Z is our P.
times-
No, what is Z? Sorry. What is
integer numbers.
Yes, but what is the example of? Excuse me.
So we want to consider Z, okay, as a semi-field with the product equal to the
So it is
regular
our
addition.
P. No, you have to
P.
you have to help me.
Yes.
You are considering a special case. No?
No, it's not a special case. You consider this semi-field, okay, and we want to express this formula in terms of this semi-field structure.
So Dm is an integer?
Dm are integers, yes.
Ah, that is right,
Dm
right.
are
They are the exponents. I see. So you're writing with the. You're just changing the notation. That is
Yes.
not
So
important.
the
Okay.
product is the plus, and the additional sum
Yes,
is the
yes, yes.
maximum. So
Yeah.
Dm plus 2 it becomes Dm times Dm plus 2.
It's a change of notation. No, it doesn't. Yeah, because you're dealing with exponents, so this is.
Yes, and
Very-
the maximum here
Raised to the power of.
becomes 1 plus, so this is Dm plus 1
No?
plus 0, which is the identity with respect to the product of this semi-field.
You
we
forgot.
denote it by 1
Ah, by
Pm. Well, this is ambiguous. Maybe we denote it by E.
the identity.
The identity with respect to the product, which is the 0, the element 0 in here.
Right.
And this product becomes an exponent.
Right. Exponent. Right.
So they were the same. So they were not really the same, but this is a particular case of this because.
Yes.
Okay. This can be seen as this formula.
Okay.
And we saw last time.
In what sense particular case? Help me with this, because was defined as.
No, it's not a particular case. I mean,
no.
This can be reinterpreted like this formula.
Yes.
Which is formally the same as this.
But it's not a special case.
No, it's not.
Okay.
It's not a special case.
So that is ordinary multiplication there, right?
Yes.
U1 times U1
Yes.
So it's.
Yeah.
It's like this with respect to the semi-field.
I mean, what do you mean ordinary multiplication? You have to know that you are in the crazy madness of the p, right?
Yes.
So ordinary means nothing. I mean, this is a strange thing.
Yes.
That's the truth.
Yes. It's the product in the group.
It says ordinary nothing because this p can be a crazy thing.
The product of the group P.
I wouldn't call it ordinary.
Yes.
Okay.
But last time we saw that in our case the UN are periodic using this relation.
Ah, I see.
Okay. So for any semi-field structure. Okay. So this implies that also the DM are periodic because they satisfy this recursion with respect to a semi-field structure on Z. So DM are periodic with respect to a periodic of period H plus 2. Final observation before proving this is that also Bn is periodic of period H plus 2. This is a trivial observation because so if H is even, this is obvious. There's nothing to say here. If H is odd, this is not trivial, but if H is odd, this happens in the only case where B1 is equal to B2. So all these elements are. So the period is not the minimum period, it's just a period. Okay.
I see. So it's not a minimum one, okay.
So this is a stupid observation that we use to make a unified proof for the 4 cases. Not really. We do one case.
So it's one
apart.
case. Yeah, I see. So it's a case by case analysis after all. This is the truth.
Yes, which will be presented formally as a unique proof.
I know, but it's not.
No. We are using that. We know that we are
Yes.
in one of the 4 cases. Okay. So now we have to prove that this product is 1. We make it before one special case, which is the A1 times A1 case, where B1 equal B2 equals 0. In this case, H is 2. Yes. And from this relation, we have that UN is UN plus 2 minus 1, because the product is 1. And also here we bn plus bn plus 2 is 1. Yes, and this computation becomes rather trivial. You have to make
Okay,
this
so
product.
We are examining all the cases separately?
No,
I don't
just this
understand.
case separately, and then we do the other 3 cases together. This is a special case where this.
I'm very confused on the streamline of the proof, because now we sort of went back to the case of rank 2. I don't understand.
No, we have these 2 numbers b1 and b2 that can be either 0, 0, 1, 1, 1, 2, or 1, 3.
Yes.
Yes. So we have to consider these 4 cases. These were the 2 entries in the original matrix.
I see. So the h plus 2 actually can assume only those values, not any value, just those. Okay.
So yes, the value of h was described in the first table.
Okay. Then we have this extra little thing that we can have another path at each step. That's what we are allowing. Yes, the U3. I mean, you can have, we're just allowing this little thing.
Yes.
A little departure from the rank 2 case.
And so in this case, you have to substitute this and express everything in terms of U1, U2, and D1 and D2, and everything cancels. So, yes, I don't want to do this computation. It's just 3 lines, but it's very stupid. So maybe we can do the general case directly. Okay. So we have to prove that this is 1, and we consider this product h plus 2 n plus 1 bn 0 minus m. And we put an exponent here, b1 times b2. Remember that the group P is torsion free, so to prove that this is 1, it's enough to prove that this power is 1. Okay. So let's see what we have. Product n from 1 to h plus 2 u n plus 1 where I am. Yes, I want to write whatever I need. Okay, u n plus 1 to the maximum between bn 0 times b1 b2. Yes. And then here I use this relation so that we know that u1 plus un plus 1 to bn is the left hand side. So depending on the parity, you can use either b1 or b2. So what remains is n plus 1. So this becomes un plus 2 to minus bn plus 1. Okay? Then
Why bn plus 1? Why not bn? I'm confused.
yeah, because,
Because-
1 plus plus 1 2 bm
Ah,
is times plus 2. So I use the one of these two, which is and what remains is bm plus 2.
okay. Yes.
Yeah, so now I want to look at the exponents of all variables ui. So we start from u1. So u1 appears here only with m equals 1 here. So its exponent is minus b1 b2. And we look at u2. So u2 appears here when m is 1. So the exponent maximum b1 0 b1 2. Yes, and then it appears also here when m is 2. This is minus b2 b1. Then all the variables from 3 to h can be treated together. So un comes with exponent I don't know, but I wrote this from yes, from 1 to h, and then I write un plus 2 here. So that the exponents un plus 2, I write what I copy what I wrote on my notes. I hope this is correct. Dn plus dn plus 2 minus dn maximum 0. Okay, so let me see. Minus bn plus 1 dn is this. And then minus bn plus 1 times bn plus 2. We obtain this as an exponent of un. The index is smaller than 2, and then this we will figure this. Then we have the last two elements, which are h plus 3. This is similar to the case of u1 and u2. This is h plus 2 times h plus 1 maximum